Right. Good evening, my dear students. Welcome to the ECE Engineering Academy and APL program. APL stands for ACE Preparation League. I am Ravindra Reddy from ACE Engineering Academy. Now today in live session class, I am going to discuss about the expected or most expected models from complex variable topic, and which is the one of the subtopic of mathematics part, In this complex variable, whatever we discuss the models, which are the most expected questions only and most expected models. Now, before going to start let me explain about the subtopics of this complex variable topic on. Now it is a complex variable topic. In this complex variable topic, we have the 4 subtopics. Very first one is analytic functions. Second one is complex integration. Third one is complex power series. Last one is also complex integration by residue theorem only. In the analytic functions, we'll discuss about the problems on or problems related to differentiability, analyticity, and singular points. Next, we come to the second subtopic. In the complex integration, we'll discuss about the problems on complex integral by the 2 theorems, Cauchy's integral theorem and Cauchy's integral formula. After that, we go to the complex power series. In the complex power series, we have the 2 types of series. One is Taylor series and Laurent series only. So we do the problems on Taylor series and Laurent series. After that, we go to the last subtopic, complex integration. The second subtopic and last subtopics are same topics, but in the second subtopic, we do the problems on, that is, we do the problems on complex integration by Cauchy's residue theorem and Cauchy's integral formula and Cauchy's integral theorem only. But in the last subtopic, we try to discuss about the problems on complex integral and by residue theorem only. Okay. Already we have the 2 theorems in the complex integration second subtopic, Cauchy's integral theorem and Cauchy's integral formula. But we cannot do all the problems by these 2 theorems only. So in such case, we go to the modified theorem only. The Cauchy's residue theorem is the modified theorem of the Cauchy's integral formula, and residue theorem is a powerful theorem only. It is not only useful for the evaluation of complex line integral, it is also useful for evaluation of the real improper integrals also, right? That is why first we discuss about the complex integration by 2 theorems in the second subtopic, and then we go to this last subtopic only. But for this, we should know how to find the residues, or how to evaluate the residues, how to calculate the residues for a given function at a singular point. For that, again, we require the complex power series. In this, we should know how to expand the function as an infinite series. That will be Taylor or Laurent series only. But for finding the residues, we require only the Laurent series only. Right? Now, let us start the today's class. Now, we go to the first problem. Now, this is the problem. The function is given in terms of x and y, and it is a complex function. This is given along with 4 options. In the first option, it is given that differentiable only at origin. This is 0. Actually, it is written as 2, 0, not at 2, 0, origin 0, 0 only. Next, analytic only at 0, 0. Third option, everywhere analytic. That means at every point in the total complex plane or whole complex plane, the function is analytic. Next, nowhere analytic. Nowhere analytic means it is not analytic at any single point in the total complex plane only. So these are the options only. Now here first we check the differentiability. To check the differentiability, we need to check the 2 conditions at a single point. If you want to check the function is differentiable or not at any single point, at that point we need to check the 2 conditions. The first condition is CR equations, that is Cauchy-Riemann equations, and other condition is continuity of the functions only. Let me explain that one. So if you want to check the function is differentiable or not at a particular point z0, at this point we have to verify the two conditions. One is the CR equations, two CR equations, ux equal to vy and vx equal to minus uy. These are the two CR equations, Cauchy-Riemann equations. It is a first order partial derivative of u with respect to x. It is a first order partial derivative of v with respect to y. Similarly, other two only. Next, other condition is the continuity of the functions u, v, ux, uy, next vx, vy. We require the continuity of these functions. If these two CR equations satisfy at this point, and also these are continuous at this point, then we can say that function is differentiable only. We can say that function is differentiable at a single point z0. Suppose the function is differentiable at a point z0, then we can check the further condition analyticity or analytic function or not. If you want to check the function is analytic or not at a particular point, at this point we check differentiable or not. If it is differentiable at this point, we consider some neighborhood about this point. We consider neighborhood about this point. We can take small neighborhood. In general, neighborhood means very small distance only. We can take the small neighborhood or little bit larger neighborhood, but for appearance we are taking the bigger neighborhood here. In this neighborhood, at every other point also these conditions satisfy, we can say function is analytic at this point only. That means if a function is differentiable at a point z0, at every other point also differentiable, then only the function is analytic at that point only. So the difference between differentiability and analytic is, at a single point z0 derivative exists, we can say differentiable at that point only. Next, if a function is differentiable at a point z0 derivative exists, and also at every other point in the neighborhood also derivative exists, then the function is analytic at a point z0 only. Okay? So first we check the differentiability for this function, right? To check the differentiability, first we need to know the real and imagined parts of this complex function. After that we find all the derivatives and then we verify the conditions only. Now let us start the solution of the problem. Let u plus iv equal to f of z, then u equal to f of z is this function. If we compare this given function with this, we can get the u as x cube minus 3xy square plus x, and v equal to 3x square y Let me write once again, f of z, u equal to x cube minus 3xy square plus x, v equal to 3x square y minus y cube plus y. Now these are the real and imaginary parts of the function f of z only. Now next we require the first order partial derivatives of these, which implies ux equal to, with respect to x partially. When you differentiate this partially with respect to one variable x, we treat other variable y as constant, 3x square minus 3y square plus x, derivative is 1, uy with respect to y minus 6xy, next vx equal to, v with respect to x, with respect to 6xy, next v with respect to y equal to, from this v, 3x square minus 3y square plus 1. Now we have the uv and first order partial derivatives of these two with respect to both variables x and y only. Now we check the CR equations. The first CR equation or Cauchy-Riemann equation is u suffix x equal to v suffix y only. Ux is this function and vy is this function. Ux is this and vy is this. These two are same. These two are same. Whenever these two are same, we check whether these two are same only at one point, some points, at all points. Depending on that, we can set differentiable at one point, some point, at all points only. But here, these two are same at every point only. These two are same because these two are same functions. On both sides same function, whatever you substitute the point x, y here, we can substitute the same point here. Both sides will get the same value only. So these two will be same at every point only. Next, second CR equation is Vx equal to minus uy. We check whether this equation satisfies or not. Vx equal to 6xy, uy equal to minus 6xy. If we replace this 6xy with Vx, then we can write Vx equal to minus uy. So this equation is also satisfied. These two are satisfied not only at one point, they are satisfied at every point. At every point means in the total complex plane, these two will satisfy only because of the same functions, same only. Whenever these two satisfy at every point, then we can check the second condition, that is continuity condition. Continuity condition of these functions u, v, ux, uy, vx, vy only. Now to check the continuity of these functions, we need to check the continuity of the real functions because for this complex function u and v are real functions of two real variables only. And here these are algebraic functions free from transcendental functions. So directly we can say function is continuous or not with the help of the standard functions. We have some real standard functions. With the help of that, directly we can say function is continuous. The standard functions are like this: e power ax, cos ax, sin ax, sin h ax, cos h ax, and the polynomial of the form a0 plus a1x plus a2x square plus and so on plus an x power n, and n belongs to positive integer only. 1, 2, 3, 4, 5. 5 transcendental functions, 1 polynomial. These 6 functions are everywhere defined, continuous, differentiable, and also integrable. These are the real standard functions only. So with the help of this, directly we can set these functions continuous or not only. But here, all these are in the form of this form only. So using this standard function, we can set directly continuous or not only. Using this, the standard function, we can set continuous or not here. Now let us start with the u. It is a sum of 3 functions, 1, 2, 3. Here we have x cube. X cube is the next term. It is continuous at every point. It is also polynomial, second term, continuous at every point. In this we have a product of 2 terms. 3x is, this is a term, a1x form, and y square is like this. So it is a continuous, it is also continuous. Continuous, continuous, product is continuous. The sum of all these also continuous at every point only. Similarly, continuous, 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 continuous. Again, sum is also continuous because every term is a polynomial only. And this 1 is a constant polynomial, a0, very first term. Other terms are absent only. This is a term from a0 only. So continuous, continuous, continuous. The total function is continuous only. 6x is continuous, y is continuous, it is also continuous at every point. 6x is continuous, y is continuous at every point. This is also continuous. Similarly, it is also continuous because already we know that it is a continuous ux is. So these are the continuous functions at every point because all are polynomials only. We know that polynomial is continuous at every point only. So that is why. So here all the functions u, v, ux, uy, vx, vy. These functions are continuous and these two equations are satisfied at every point in the whole complex plane. Therefore, this function is analytic at every point, or this function is differentiable at every point. Whenever function is differentiable at every point in the whole complex plane, you take any point, at that point derivative exists, in the neighborhood also derivative exists. That is why at every point differentiable means at every point the function is analytic. That is why the option C is correct on it. Everywhere analytic on it. So what we have done here, for a given function, we have taken like this u plus iv equal to f of z for finding the u and v. After that we have done the first order partial derivatives. After that we verified the CR equations. But here these two are satisfied at every point. So next we check the continuity like this. But here these are also continuous at every point. So finally these two conditions are satisfied at every point in the total complex plane. That is why the function is differentiable at every point. Because of differentiable at every point, the function is everywhere analytic. So because of this, option C is correct. This is about problem number 1. Now we go to the next problem. Now this is the second problem. The function f of z is z into Re of z. Re of z means real part of z. Now for this function we are given 4 options. Differentiable only at origin 0, 0, analytic only at origin 0, 0, everywhere analytic, analytic only at 3, 4 only. Like previous problem only. So first we need to find the real and imaginary parts of this function. After that we find the first order derivatives and then we check the CR equations only. Let us start the solution. Let f of z equal to u plus iv equal to z into Re of z. Then u plus iv equal to z is x plus iy into real part of z is x. Z equal to x plus iy. From this we can say it is a real part of z and it is the imaginary part of z only. Now this is equal to x y plus I x square plus I x y, which implies u equal to x square u equal to x square and v equal to x y. Next, the first order partial derivatives are ux equal to 2x, uy equal to, with respect to y, derivatives 0, vx equal to y, vy equal to x. These are the first order partial derivatives only. Now we check the CR equations only. The first CR equation is ux equal to vy or not. Here ux is 2x, vy is x, but these two are not same like in previous problem. In the previous problem directly the CR equation was satisfied directly, but here it is not same only. Whenever CR equation is not satisfied directly like this, we check whether these two are equal at any value of x and y or not. Now here we can equate these two at x equal to 0 only. Right? Next, the second CR equation is Vx equal to minus uy. Here Vx is y. Here Vx is y equal to minus uy is 0. Now this equation will satisfy only for y equal to 0 like this only. So these two equations will satisfy only x equal to 0, y equal to 0. That means we can say that the CR equations are satisfied only at origin only. Only at origin only. In the total complex plane, only at origin, the two CR equations will satisfy only. That is, we cannot equate these two at any other value of x. We cannot equate these two any other value of y only. So finally we can say these two will satisfy only at one point origin only. Next, whenever the CR equation satisfy at the origin, we can check the continuity of the functions also at the same point. U is a polynomial function continuous at every point. Product of two functions, x is a polynomial, it is continuous, y is also continuous. Product of two continuous is continuous, it is a polynomial continuous, constant polynomial continuous, it is also continuous, x is also continuous. All these are continuous at every point. But we need to check the continuity only at a single point on. Whenever these functions are continuous at every point, at a particular point origin also continuous only. So at a single point the CR equations are satisfied and the functions are continuous at this point, then the function is differentiable at that point. But the CR equations do not satisfy at any other point in the total complex plane, only at origin only. Because of this, we can say that function is differentiable only at origin, not at any other point only. So that is why differentiable only at origin is correct only. Here ux equal to vy and vx equal to minus uy only at origin 0, 0 only. And anyhow these functions are continuous at that point. Therefore we can say that the function f of z is f of z equal to u plus iv is differentiable only at origin 0, 0 only. So nowhere differentiable in the total complex plane except this point only. That is why the first option is correct. This is about problem number 2 only. Next we go to the third problem. Which of the following function or functions is oblique or not analytic in this region where z is a complex variable? In every option one function is given. We need to choose the function which is not analytic. The function which is not analytic. That means if the function is not analytic means the function will have a singular point only. Any one of the function from the options has singular point in this region, then that is our correct answer. If it is analytic in this region, that is not a correct answer. We are asked to choose a not analytic function only. If a function is not defined, if a function is not defined at a point z0 or not differentiable or not analytic at this point, then we can say function is having singular point at that point only. At any point the function is not defined, not differentiable, not analytic, then the point is called singular point of the function only. Let us start the solution. Here the given region is mod z less than or equal to 2. Now it is in the form of like this, modulus of z minus z0 equal to r. This is the equation of this circle in terms of z. It is the equation of circle in terms of z only. The same equation of circle in terms of x and y is x minus x0 whole square plus y minus y0 whole square equal to r square only. It is the equation of circle in terms of x and y. It is the equation of circle in terms of z only. Suppose if we write the inequality like this, mod z minus z0 less than r. This inequality says that it is interior to the circle mod z minus z0 equal to r. Or if you write the mod z minus z0 greater than r, this greater than inequality says that the point z lies outside the circle or this is exterior to this circle only. Suppose if we have like this less than or equal to, this says that the interior to the circle and on the circle, boundary and interior both together only. So we are given the mod z less than or equal to 2 means we can write the mod z less than or equal to 2 as like this, in this form. That is mod z minus 0 less than or equal to 2 only. If we compare this with this, center z0 is 0, origin, radius is 2 only. So first we draw this circle and we check the singular point of the function is inside the region, on the region or outside region. Based on that we can choose the not analytic function. Center is 0, radius is 2. This is our circular region. But mod z less than or equal to means inside the region, on the region. We consider the inside the region, on the region, boundary also only. Now let us start with the first option, option A. In every option, function is given in terms of z only, and that this function is in the form of something by something or numerator by denominator only. If you observe the only numerator function, it is a polynomial, it is an exponential function. In the first problem, I have shown the standard real functions. Like that, in the complex also we have the standard complex functions. The functions in complex variable are like this: e power a z, sin a z, cos a z, sin h a z, cos h a z, and every polynomial a0 plus a1 z plus a2 z square plus and so on plus a n x power n, z power n. And n should be positive integer or natural number only. 1, 2, 3, 4, 5, 6. These are the complex standard functions, these are the complex standard functions, just like our real standard functions only. All these are with the complex variable. There we have written it with the real variable only. Exponential, sine trigonometric, cos trigonometric, sine hyperbolic, cos hyperbolic. These are the transcendental functions and it is polynomial only. These 6 functions are at every point defined, continuous, differentiable, analytic also only, at every point, right? So with the help of this also we can say directly the function is analytic only. Now let us consider the first option function. Now this function is in the form of something by something or numerator by denominator. In the numerator, sum of 2 functions. Z is polynomial, everywhere analytic. E power z is everywhere analytic. Sum of these 2 is also analytic. When 2 functions are analytic, sum of the 2 functions is also analytic on. In the denominator, z minus 3 is a polynomial. It is also analytic at every point. Analytic everywhere. But if you consider the total function, z plus e power z by z minus 3, the total function is not defined at z equal to 3 only. For the existence of this ratio, the denominator part must be not equal to 0. But denominator is 0 only at z equal to 3. So the function is having singular point at z equal to 3 only. This function has singular point at z equal to 3. But this singular point is not inside the region. It is lying outside the region because 3 is outside the region only. So whenever function has singular point outside the region, within the region, on the region, this function will be analytic only. It is not analytic only at z equal to 3. That 3 is outside the region only. So within the region, on the region, the function is analytic. That is why we never choose this. This is a wrong answer because we are asked to choose a not analytic function only. Next, problem option B, second option. The same problem, second option. It is a polynomial everywhere analytic. It is a polynomial everywhere analytic. Analytic. The total function will be analytic when the denominator is not equal to 0. But denominator is 0 only for z equal to 1. So this function is defined for all values of z except z equal to 1. At z equal to 1, the function is not defined. Not defined at z equal to means z equal to 1 is a singular point. This function has a singular point at z equal to 1 and z equal to 1 is inside the region. The function has singular point at z equal to 1 inside the region. So whenever function has singular point inside the region at one point, this is not analytic. This function is not analytic in the region. So it is our correct answer. Next we check for other options also, because here it is given that is or. Next, the function is 1 by sin z. 1 by sin z. Only 1 is constant polynomial at every point analytic. Only sin z is also analytic at every point. But if we consider the 1 by sin z, the whole function is not defined when sin z is equal to 0. But zeros of sin z are, the zeros of sin z are n pi, comma, n belongs to integers. That is for n equal to 0, 1, 2, 3, minus 1, minus 2, minus 3. Finally, z equal to 0, minus pi, plus pi, minus 2 pi, plus 2 pi, and so on. These are the zeros of sin z, which are the singular points of main function. So at these points, this function is not defined. At this point, the function is not defined means all these are singular points only. All these are singular points. In particular, these are z equal to 0, plus or minus pi, plus or minus 2 pi, and so on. These are the particular points, general particular one. Out of all infinitely many singular points, one of the singular points z equal to 0 is inside the region only. So within the region, this function is having singular point. This function is having singular point within the region. Therefore, the function is not analytic within the region. So it is also our correct answer. Next, we go to the last option of the same problem. Here the function is exponential function, but we know that exponential function is at every point analytic. Exponential function is of this form, is analytic at every point, but it is not in the form of this. In place of a z, we have some other function. This total function becomes infinite when 1 by z becomes infinite. The analyticity depends on this function 1 by z only. But we know that 1 by z is not defined at a z equal to 0. When function is not defined at z equal to 0 means it is having singular point at z equal to 0. At z equal to 0, this becomes infinite. E power infinity also infinity. E power infinity is also infinity at z equal to 0. So this function has singular point at z equal to 0. That z equal to 0 is inside the region only. From option D, the singular point is z equal to 0. Right? This singular point is inside the region. So this function has singular point inside the region, so the function is not analytic in the region. This function has singular point in the region, so the function is not analytic. This function has singular point inside the region, so it is also not analytic. But this function is having singular point outside the region only. So out of 4 options, B, C, D are correct, because these are not analytic inside the region. So from this we can set more than one answer is correct, more than one. So this problem comes under multiple select questions or multiple correct answer questions only, because more than one option is correct only. So just find the singular point of each option function and check whether that is inside the region, on the region, or outside the region. But we are given region inside the region, on the region only. So from B, C, D, the singular points are inside the region. That is why these are the correct answers only, not analytic functions. This is about problem number 3. We go to the next problem. Now, in this problem, for some analytic function, imaginary part is given. For some analytic function, imaginary part is given V. And we are asked to find the real part. In this analytic function, the general form of analytic function is f of z equal to u plus iv. In this problem, we are given imaginary part. For given v, we need to find the real part u only. or if u is given we can find v, or v is given we can find the u. Any one is given we can find other one. Here given v we can find u. To find u we consider its total differential du. The total differential of u of two variable x and y is given by du equal to ux dx plus uy dy. Du equal to ux dx plus uy dy. It is the total differential of u only. Why we are considering like this means just by integrating this function we get the, by integrating this du we can get the u only. So to obtain u we take this result and we integrate on both sides only. Now for this we require the derivatives of this function only. So let us start the solution. Now given v equal to e power minus y into sine x. For this we need to find the u. Let us find the first order partial derivatives of this function. V with respect to x equal to cos x into e power minus y, and v with respect to y equal to minus e power minus y into sine x with respect to x with respect to y. Now to find u we consider differential of u. Consider du equal to ux dx plus v uy dy. Now we need to substitute the function ux and uy, but ux uy are not known because first of all u is unknown function. When u is unknown, ux uy are also unknown functions only. Now we try to change these two unknown functions with known functions with the help of the CR equations. Between the known and unknown we have two relations through CR equations. So through CR equations we change these two unknowns only. We replace these two with known functions. Du equal to ux. By first CR equation ux equal to vy dx plus by second CR equation vx equal to minus uy. So in place of uy we are the vx. Next we substitute these two functions. Du equal to in place of vy minus e power minus y into sine x dx plus vx is minus e power minus y into cos x dy. After replacing the unknown function with the known functions, we can substitute both and then we can integrate. Now before integrating each and every term, just observe the right hand side. Function of x and y dx, some function of x and y dy only. Something dx plus something dy only. We check whether these two are written in the form of only single term only. If you are able to write the sum of the two terms as a single term, then we can go for direct integration only. Just look at this. D by dx of uv equal to the derivative of product of two functions. First function into derivative of second function plus second function into first function derivative. Derivative of product of two functions. Or differential quotient or change in one quantity correspond to change in other quantity only. Suppose if we have like this du d of uv equal to, we write the differential of product of two functions similar to this. The first function into differential of second function plus second function into differential of first function. It is derivative, it is differential. Change in one quantity correspond to change in other quantity. Here change in only one quantity only. Now here whatever we have this is directly in the form of like this only. These two terms are in the form of these two terms. Cos x differential d of cos x is same as minus sin x into dx only. Again, e power minus y differential is differential of e power minus y is minus e power minus y dy, right? So cos x differential is minus sin x dx and e power minus y differential is minus e power minus y dy only. So finally, we can write these two together as differential of some function only, according to this. du equal to d of e power minus y into cos x. Just like d of uv form only. Now we have differential and we can take the integration on both sides plus integral constant k or c, we can write any one. Integral of this is just like integral of 1 dx is x, like that integral of 1 du is, therefore its integral is u equal to integral of this is integral of 1 d of this function is the same function e power minus y into cos x plus constant. This is our required function u or real part of the given analytic function only. And this is given in one of the option e power minus y cos x, that is option A is correct only. With a constant, for particular value of constant k, the function is given here only. For k equal to 1, this is given. So given v, we can find u, or given u, we can find v. Any one is given, we can find other one by following same procedure on like this. This is about this problem. The solution is completed. Next, we go to the next problem. Here, real part of some analytic function f of z is given, and we are asked to find the analytic function. For some analytic function f of z equal to u plus iv, real part is given. For given real part of this analytic function, we can find the function f of z, or for given imaginary part of this function also we can find the f of z. Given any one part, we can write the main analytic function only. But in this problem, we are given real part only. Finding the function f of z is same as finding the u plus iv only. That is, we require the real part and imaginary part only. Already real part is given. For a given real part, just like previous problem, if we can find the v, we can substitute both u and v here. That will be the required analytic function. Or other way also we can find the same analytic function. We can do this problem in two ways. Just like previous problem, from given u, we can find v. After that, we substitute these two in these two places on. Then we get the function in terms of x and y. Because u is in terms of x and y, v is also in terms of x and y. After getting the function in terms of x and y, we replace x by z, or replace x by z and y by 0 only. So that directly we get the function of x and y in terms of z only. That is one method. But here, we do this problem by other method. Let us start the solution for this. One method is just like previous problem method only. Now here we are applying the another method only. Given u equal to x cube minus 3xy square plus 3x square minus 3y square plus 1. Given u, first we need to find the two first order partial derivatives ux and uy. Ux equal to 3x square minus 3y square plus 6x and u with respect to y is minus 6xy u with respect to y is minus 6xy minus 6y. Now, to find the function f of z, we consider the derivative formula f dash of z f dash of z equal to ux minus I uy. Now substitute ux uy. F dash of z equal to ux is 3x square minus 3y square plus 6x 3x square minus 3y square plus 6x. From this, u with respect to y minus 6xy minus 6y, minus minus is common, plus I into 6xy plus 6y. Substitution is completed on. Next, it is a function in terms of x and y on right hand side only. If you want to get this f dash, if you want to get this f dash z in terms of z on right hand side, if you want to get this function in terms of z, replace x by z, y by 0 only. Because left hand side we have a f dash z, that is d by dz of f of z only. So if you want to get f of z, we should eliminate this d by dz only. To eliminate d by dz, we should integrate both sides with respect to z. But left hand side it is in terms of z, right hand side it is in terms of x and y. We cannot integrate both sides with respect to z. That is why we try to express right hand side in terms of z. Because of this analytic function, we replace x with z, y with 0. On right hand side, after replacing x with after replacing x with z, y with 0, this function becomes 3z square plus 6z plus 0 plus 0. Finally, it is a function. After replacing x with z, y with 0. Now take the integration on both sides. Therefore, integral of this is f of z equal to z cube integral, z square integral is z cube by 3, 3 get cancelled. So after integration, this function is z cube plus z integral is z square by 2, 2 3 times 3z square plus integral constant. We are integrating with respect to integral, we are integrating both sides with respect to complex variable z. That is why this constant must be complex constant only. And c must be in the form of c1 plus I c2 only. Right? This is the required, the function f of z in terms of z only. This is our correct answer on. This is about the problem. Now we go to next problem. It is a complex integral. We are given integral along with function like this. And we are asked to find the integral along the curve C. C is given by this. Already we know that it is the equation of the circle mod z minus z naught equal to r equal to 2, z naught is 1. Center is 1, radius is 2 1. Now to evaluate the integral of this complex function, we have two theorems. One is Cauchy's integral theorem, other one is Cauchy's integral formula. Now let me explain about that Cauchy's integral theorem statement and Cauchy's integral formula statement on. Later, depending on both, we can do the problem. Cauchy's integral theorem. Whenever the function f of z is analytic at every point, the function f of z is analytic at every point inside and on a simple closed curve C. Inside the closed curve, on the closed curve, the function is analytic. That is, analytic means the singular points of this function should not lie inside the region, on the region. That may lie outside the region only. So whenever the function is analytic inside C, on C, at every point, then the integral of f of z dz equal to 0 along that closed curve only. If you are asked to find the integral along the closed curve, first we check the total function, given function f of z is analytic at every point inside C, on C or not. Suppose the function is analytic at every point inside C, on C, integral along that is 0 only. This is about the Cauchy's integral theorem only. Next, Cauchy's integral formula. According to Cauchy's integral formula, the function should be in the form of like this. F of z should be in the form of some function of z by z minus z naught power 1, or function phi of z, some function phi of z by z minus z naught power n. The function should be in the form of something by z minus z naught power 1, or something by function like this one, z minus z naught power n only. In this form or in this form is like this. If this function is in this form or in this form, then we verify the two conditions. Whatever you take the function in the numerator, phi of z, this phi of z should be analytic. This phi of z should be analytic at every point inside C, on C only. On the curve C, inside the curve C, at every point the function phi of z should be analytic. Function phi of z should be analytic only. This is the first condition. Next, from the denominator, this point should lie inside the region or inside the closed curve C only. The point z naught should lie inside the region, and the numerator function should be analytic inside C, on C only. These are the two conditions for this function. According to Cauchy's integral formula, the function should be in the form of like this, something by z minus z naught, something by z minus z naught power n. The conditions are there, two conditions. For numerator, one condition; for denominator, one condition. Denominator means the point z naught should lie inside the region, and the numerator function should be analytic inside C, on C only. That is the condition. If these two conditions satisfy, we can write the integral using this formula. Integral over C f of z dz equal to integral over C phi of z by z minus z naught z minus z naught dz equal to 2 pi I into phi of z naught. We substitute this z naught point in the numerator function and multiply with 2 pi. This is the value of the integral. The function should be in the form of some function phi of z by z minus z naught power 1. After that, we verify the conditions. This function is analytic inside C, on C. The point is inside the region. Then the value of this integral is given by 2 pi I into this function value at a point z naught. Next, second result is for this power n only. integral over C f of z integral over C f of z dz equal to integral over C some function phi of z divided by z minus z naught power n dz equal to. Both are same only the power is difference in the denominator only. So this is equal to 2 pi I divided by this power minus 1 factorial into power minus 1 times derivative of the numerator function at a point z naught. N minus 1 times derivative at a point z naught. It is the result of it. This is the Cauchy's integral theorem. It is a Cauchy's integral formula. For the evaluation of the integral of complex function along the closure curve, we consider these two theorems. Depending on the function, the conditions, we can apply the one of the particular theorem only. According to the first theorem, the whole function f of z is analytic inside C on C, then the integral along the closure curve is 0. That means the singular points of this should not lie inside the region, on the region. That may lie outside the region only. Next here, according to this function, the function should be like this. Some function by single factor power 1, some function by single factor power n. Both are same, but the power is different. Here power 1, here power not 1. It is a difference only. So, numerator function value at a point z naught into 2 pi. Here, the numerator function, how many times the derivative? This power minus 1 times the derivative. Here, power minus 1 times factorial. So, now, we will discuss when to apply this, depending on the problem only. If you are given some integral along the closure curve or over the closure region, with some function dz with a closure curve C or closure region R. If any integral is given along with a closure curve or closure region R, first we consider the function f of z. Whatever the function is given here, we take that function as f of z only. Next, second step, we try to find the singular points of f of z. We find the singular points of this function. That is the second step. Next, third step, we draw the region. We draw the region with a given equation of curve. We draw the region with a given equation of curve. After that, after drawing the region, we check the singular points lie inside the region, on the region, or outside the region. Based on this only, we can apply the particular theorem only. Suppose the singular points of this function do not lie inside the region, on the region. The singular points of this function do not lie Once again I repeat, first we should take the function as f of z, next we find the singular points, next we draw the region with a given equation of curve. After that we can check the singular points lie inside the region, on the region, or outside region. Inside the region, on the region, no singular point. Then in this case we apply the Cauchy's integral theorem only. Let us have a 2 minutes break. After coming back, we do the problems on this. So welcome back to the session. Now before the break we have seen this. So we take the function f of z, we find the singular points, we draw the region with the given equation of the curve. After that we can check the singular points lie inside the region, on the region or outside region. Based on that we can apply the particular theorem, Cauchy's integral theorem or Cauchy's integral formula. Suppose the singular points of the function do not lie inside the region, on the region, do not lie inside C, on C. That may lie outside the region only. In such case we can apply the Cauchy's integral theorem, the first theorem, Cauchy's integral theorem only. Suppose the singular points lie inside the region, one or more, the singular points lie inside the region, one or more inside the region. In such case we can apply the Cauchy's integral formula. No singular point inside C, on C, then we apply the Cauchy's integral theorem. Suppose singular points present, then we apply the Cauchy's integral formula. That's all. Just we follow this procedure and we do all the problems. So let us start our problem. It is a given integral along with a closed curve. What is a closed curve here? Circle equation is given. Mod z minus z naught equal to r. Let us start the solution. Whatever the function is given inside the integral, we take this function as f of z, z square plus e power z plus cos z cos z divided by z minus 4 power 2 into z plus 3 power 5. It is a function. It is the first step. After this we can find the singular points only. This exponential function is analytic at every point, cos is analytic at every point, polynomial is analytic, sum of all these also analytic at every point. In the denominator polynomial, that is analytic. But when you consider total function, the total function is not defined at 4 and minus 3. So the singular points are z equal to 4 and minus 3 only. Next, we draw the region with a given equation of curve. The equation of curve is mod z minus z naught equal to r. Zero, 1, 2, 3, 4, minus 1, minus 2, 1, 2, minus 1, minus 2 only. Now center of the circle is 1. Center of the circle is at 1. And the radius is 2 only. Radius is 2. This side radius is 2. Height is 2. Now the circle is like this. It is our given closed curve C only. Now check one by one point, inside the region, on the region, outside region only. This point 4 is lying outside the region, so we never consider this. Next, minus 3 is also lying outside region. Minus 3 is lying outside region only. This is the point. So the function has two singular points, but two singular points are lying outside the region. So within the region there is no singular point. Therefore the function is analytic inside C, on C only. Therefore integral along the closed curve is always 0 by Cauchy's integral theorem only. Therefore integral over C f of z dz equal to 0. The function has two singular points are lying outside region. Therefore by Cauchy's integral theorem we can set integral of the function is 0 along the closed curve. This is about the problem, right? The solution is completed and the option A is correct. We go to next problem. Again we are given the value of the integral. We are given the integral and we are asked to find the integral of integral value, and this is given along with the curve C. C is the equation of the ellipse, x square by 16 plus y square by 9 equal to 1, and there is no condition on the ellipse. Therefore, it is a closed curve. Because of closed curve, we try to do this problem by our theorems only. And then we follow our procedure only. Now, let us start the solution. According to our procedure, whatever the function is given inside the integral, we take that function as f of z only. F of z equal to z plus 3 plus e power z by z plus 3 only. It is a given function. Next, we find the singular point. The singular point of this function is z equal to minus 3 only. The whole function is not defined at z equal to minus 3 only. Because exponential is analytic, 3 is analytic, the sum of 3 is also analytic because it is a polynomial and exponential. In the denominator also polynomial, that is analytic only. The function is defined at every point except this minus 3 only. So at minus 3, the function has singular point. Next, we draw the region with the given equation of the ellipse only. Here, x square by a square plus y square by b square equal to 1. A equal to 4, B equal to 3, and A is greater than B. So major axis is along the x-axis, minor axis along the y-axis on. Now we draw the region. X-axis, y-axis on. A is 4, and B is 3, minus 1, minus 2, minus 3 only. It is a closed curve. Now check this singular point lies inside the region, on the region, or outside the region. But z equal to minus 3 is inside the region. Inside the region. It is a singular point. Whenever function has singular point inside the region, we apply the Cauchy's integral formula only. By using Cauchy's integral formula, we should evaluate this integral only. According to Cauchy's integral formula, the function should be in the form of like this. Some function by single factor like this. Either power 1 or power something like this. But the denominator is containing the power. What is the power here? 1. And we can express this in the form of like this. Because in the denominator we have a factor form. We can express this in this form only. So to express this in the form of like this, in the denominator we should write the z minus 3. Z minus of minus 3. I am writing the z plus 3 as z minus of minus 3 only. Now this is in the form of phi of z by z minus z naught form only. It is directly in the form of this only. Right? We can evaluate the integral by using the Cauchy's integral formula. So integral over c f of z dz equal to 2 pi I in the numerator function we substitute z equal to minus 3 on. That is phi of minus 3, which is equal to 2 pi I z plus 3 plus e power z at z equal to minus 3 only. When you substitute z equal to minus 3, this becomes minus 3 plus 3. These two together 0, e power minus 3. So answer is 2 pi I into e power minus 3 only. 2 pi I e power minus 3. B is the answer. This is about this problem. It is a solution of the problem. We go to next problem. Again we are given integral along with the curve C, and C is the mod z equal to 2 only. This is the equation of the curve C, and this equation is the equation of the circle. Because circle equation, it is a closed curve. If it is closed curve, we follow the same method only. Now let us start the solution. Whatever the function is given inside the integral, we take this function as f of z equal to e power z plus cos z divided by z power 4. The whole function is not defined at z equal to 0 only, because at z equal to 0 the function becomes infinite only. So singular point is z equal to 0. Singular point is z equal to 0. At this point, the function has infinite value. That is why it is a singular point of this function. Next, we draw the region. But whenever circular region is given, no need to draw the diagram. Without drawing the diagram, we can say the point is inside the region, on the region, or outside region only, with the help of these. The general equation of the circle is mod z minus z naught equal to r, mod z minus z naught less than r. This inequality says that the point z lies inside the region only. And this inequality says that the point z lies outside the region only. So whenever circular region is given, don't draw the diagram. Without drawing the diagram, with these three we can say that inside or outside or on only. Now if you substitute the z equal to 0, z equal to 0 here in this given region only. Now take the LHS part of this only, and substitute z equal to 0. Modulus of 0, 0, 0 less than radius. The less than inequality condition is satisfied only. Z equal to 0 is less than 2. The less than condition satisfies. We can say the point lies inside the given region only. So whenever point lies inside the region, we apply the Cauchy's integral formula only, and we write the value of the integral. To apply the Cauchy's integral formula, the function should be in the form of phi of z by z minus z naught power 1 or power something only. But we have some power for this factor only. So we should write this in the form of phi of z by z minus z naught power n form only. So for this we write like this, e power z plus cos z divided by, I am writing the z as z minus 0 power 4. So it is like this, phi of z by z minus z naught power n only. So by Cauchy's integral formula, we write the integral over c f of z dz equal to 2 pi I by n minus 1. If it is n minus 1 factorial, so 4 minus 1 factorial means 3 factorial. Next 3 times derivative, phi triple dash at a point 0. That is 2 pi I by 6, 3 factorial is 6, and third derivative. We require the third derivative of this function at a particular point 0 only. E power z, first time derivative is e power z, second time also, third time also the same function. This is third derivative of this function e power z. Next cos z, first time derivative minus sin z, next time derivative minus cos z, next time derivative cos becomes minus, minus minus becomes plus sin z only, plus sin z at z equal to 0. Now we require the third derivative of this function phi of z at z equal to 0 only. When you substitute z equal to 0, this becomes 0, sin 0, 0, e power 0, 1, 2, 3 times. So answer is pi I by 3 only. Now this is given in option C. So C is the correct answer. So just we find the singular points and check the singular point is inside the region, on the region, outside region. Based on that, we can evaluate the integral by using the one of the theorem only. This is about this problem. We go to next problem. Again, we are given integral along with C, and C is the equation of the circle like this. We are given equation of the circle. Again, we follow the same method because it is a closure curve, and then we follow our same procedure. And based on the singular point in the region, on the region or outside region, we can apply the particular theorem only. So let us start the solution. According to our method, whatever the function is given here, we take that function as f of z f of z equal to cos z divided by z plus 1 into z plus 2 only. It is a given function. Next, we need to find the singular points. The whole function is not defined at minus 1, minus 2. So the singular points are z equal to minus 1 and minus 2. Next, the region will be bounded by the curve mod z plus 1 equal to 1 by 2. Equal to 1 by 2. Next, we check 1 by 1 singular point, whether it lies inside the region, on the region, outside region only. If we substitute z equal to minus 1 here, minus 1 plus 1, 0. 0 is less than 1 by 2. So this point lies inside the region. This point lies inside the region. Next, minus 2. If we take minus 2 here, minus 2 plus 1, minus 1, modulus of minus 1 plus 1 is greater than 1 by 2. So this lies outside the region, not required on. So out of two singular points, one of the singular point is inside the region. The function may have one singular point inside the region or more than one also inside the region. But in this model, the function has many singular points. Out of all, only one point is inside the region only. Once the singular point lies inside the region, we should evaluate this by using Cauchy's integral formula. But according to Cauchy's integral formula, the function should be like this only. The function should be in the form of any function by single factor. It is a condition. Either power 1 or power n, any one. That doesn't matter only. But it is a function with the two factors in the denominator. So directly we cannot apply only. Now here we should express this in this form. After that only we can apply only. Now here onwards, to write this function in this form, we can go for two methods only. One method is using partial fractions. Other method is without partial fractions only. Here I will show you how to do this by two methods only. We can apply any one of the method, but better to apply the without partial fractions. That is a simple method only. So first we do this problem by partial fractions only. Method 1. Now to get the sum function by single factor, we split into partial fractions only. To split into partial fractions, let us consider only the algebraic function. After splitting this into partial fractions, we multiply with this function cos. Here the partial fractions are 1 by z plus 1 1 by z plus 1 into z plus 2 equal to 1 by z plus 1 minus 1 by z plus 2. Now, these are the partial fractions of this one. After splitting into partial fractions, we multiply with the cos function. We multiply with the cos function on both sides. Next, we take the integration. Integral over c, the function dz. Integral over c, function dz. Integral over c, function dz. Like this. Now, if you observe the both integrals, this function is in the form of some function phi of z by single factor, some function phi of z by single factor only. Right? Now, we evaluate each one by using one of the theorem only. But if you, for this function, the singular point is minus 1 is inside the region. So we evaluate the first one by using Cauchy's integral formula. And when you come to the second one, this function has singular point at minus 2. The singular point minus 2 is not inside the region only. So for second one, we apply the first theorem, and for this we apply the second theorem only. Now we write its value. This is equal to, by Cauchy's integral formula, 2 pi I into, in the numerator function we substitute z equal to minus 1. Now from the Cauchy's integral theorem, this function integral is always 0 because the whole function is not having singular point inside the region, it is having singular point outside the region only. Now this value is 2 pi I into cos of minus 1. This is the value of the integral. So answer is A only. This is by partial fractions method only. Now we do the same problem without partial fractions only. We do the same problem without partial fractions. Method 2. Our aim is expressing the function in the form of phi of z by z minus z naught. Write in our given function in this form only. The condition is this function should be analytic inside the region, on the region, and this point should be inside the region. That is the condition. Now I am taking the function f of z equal to cos z divided by z plus 1 z plus 1 into z plus 2 only. Out of two singular points, only one of the singular point is inside region only. That singular point is coming from this factor. The singular point is coming from this factor only, not from this only. So rest of the term is analytic inside the region. That is why we take this as numerator function only. This is equal to cos z divided by z plus 2. Cos z by z plus 2 divided by z minus of minus 1. Now this form is present here on, because this function is analytic inside the region, on the region, and this point is inside region. So directly we can apply the Cauchy's integral formula for this. So integral over C f of z dz equal to 2 pi I, inside the numerator function we substitute z equal to minus 1 only, cos z divided by z plus 2 at z equal to minus 1. So this is equal to substitute z equal to minus 1, cos minus 1, z equal to minus 1, this becomes 1. So answer is 2 pi I into cos of minus 1. This is the value of the integral. So same answer. If you apply the partial fraction method, or if you apply without partial fraction method, we get same answer. The simple method is second method only, because splitting into partial fractions is not an easy in some cases depending on the powers of the factors. That is why better to use this function only. So this problem is completed. We go to next problem. Now again we are given integral along with a curve C, and equation of the curve is mod z plus I equal to 1. It is also equation of the circle. Because of the closed curve, we try to do this problem by the two theorems depending on the problem only. Let us start the problem. Take the function f of z equal to z plus 1 divided by z square plus 1. The singular points of this function are z equal to plus I comma minus I. Now we check one by one. Any one of them lies inside the region, none of them lies inside the region, or any one of them lies outside the region, like this one, or both lie inside the region. If you take the z equal to I, and if you substitute here in place of this z, I plus I, 2I, modulus of 2I is plus 2, 2 is greater than this. So this is lying outside the region, not required. Next, other singular point is minus I. If you substitute minus I here, minus I plus I, 0. Modulus of 0, 0. 0 is less than 1. Out of two singular points, one of the singular point is inside the region only. So we try to do this problem by Cauchy's integral formula. But with these two singular points, we have the two factors in the denominator. Actually, the function is like this: z plus 1 divided by z minus I into z plus I. Right? It is a function. But out of these two factors, this function is given the singular point minus I inside the region, that is coming from this. So this singular point minus I is coming from this factor only. So keep this factor in the denominator and take this function as numerator function. Phi of z by z minus z naught form only. So its integral is integral over c f of z dz equal to 2 pi I. The numerator function is z plus 1 divided by z minus I at a point z equal to minus I on. Z equal to minus I. Now we substitute this. 2 pi I into minus I plus 1. Minus I plus 1 in the denominator, minus I minus I. Minus 2i. 2i get cancelled. This is equal to minus pi into minus pi into 1 minus I. 1 minus I. And if you take minus inside, then that becomes pi into plus I minus 1. This is the answer. It is similar to previous problem only. It is having two singular points. Out of two singular points, only one of the singular point is inside the region only. Now, this is the answer, and this is given in the option D only. D is the correct answer. This is about this problem. Next, we go to the next problem. Again, we are given integral of the function along with equation of the curve mod z equal to 4. It is the equation of the circle. Because of circle, it is a closure curve. With this closure curve, again we do this problem by one of the theorem or both, depending on the problem. For this function, we have three singular points, 1, 2 and 3 on. Let us start the solution and consider the function f of z as 1 by z minus 1 into z minus 2 into z minus 3 on it. It is a function. And it is having three singular points. Z equal to 1, 2, 3. There are three singular points. And the region will be bounded by the curve mod z equal to 4. Mod z equal to 4. Now we check all the singular points lie inside the region, or none of them lies inside the region, or only one of them, or only two lie inside the region, like this one. But z equal to 1 less than 4 inside the region, z equal to 2 less than 4 inside the region, 3 also less than 4 inside the region. All the singular points are lying inside the region. All are lying inside the region only. So the function has many singular points. Out of all the singular points, all are lying inside the region only. More than one inside the region only. In the previous two problems, out of all the singular points, only one of the singular point was inside the region. But here, out of three, all three are inside the region. That is more than one inside the region only. So whenever singular points lie inside the region, one or more, we do this problem by Cauchy's integral formula. But to apply the Cauchy's integral formula, this function should be in the form of like this. Any function in the numerator by in the denominator single factor only. But not single factor, it is having 3 factors only. So to express this in this form, we can use the partial fractions method or like previous problem method only. Okay? If you want to write the partial fractions method, we do like this only. One by z minus 1 into z minus 2 into z minus 3. It is method 1, partial fractions method. We do this problem also by 2 methods only. Method 1 is partial fractions only. First we split into partial fractions. Because of 3 factors, we get the sum of 3 terms. In the denominator, z minus 1 into 2, z minus 2 into 1, z minus 3 into 2 only. These are the partial fractions of these only. And we take the integration on both sides only. After splitting into partial fractions, we take the integration on both sides. Integral dz, integral dz, integral dz, integral dz only. In every integral, the function is in the form of 1 by single factor only. 1 by 2 is constant, we write outside only. This is minus 1. Now here the integral value is 1 by 2 is constant. Integral of this is z the numerator function is just 1. F of here phi of z is 1 only. So 1 at z equal to 1. That is z naught value. Next minus integral of this is, for all we are at the 2 pi I. This is equal to 1 by 2 into 1 by 2 into 2 pi I into phi of z is 1 at a point z equal to 1 minus 2 pi I into numerator function is 1 at a point z equal to 2 only. Z equal to 2 only. Plus 1 by 2 into 2 pi I function phi of z is 1 at a point z equal to 3 only. Now from each and every term 2 pi I is common. 2 pi I into 1 by 2 minus 1 plus 1 by 2. 1 minus 1, 0 equal to 0. Its value is 0 only. So answer is C only. So we have done this problem by using partial fractions only. But always the partial fractions may not be easy depending on the function only. In such case, without partial fractions also we can do the same problem in easy way by other method only. Next I will show you another method of finding the integral of this function only without partial fractions only. So we can do this problem in 2 ways. One is by using partial fractions, other one is by other method without partial fractions only. So let us go to the method 2. Method 2. The function is 1 by z now directly we write the integral over c. The function is 1 by z minus 1 into z minus 2 into z minus 3 dz equal to integral over c1 with 3 singular points inside the region. We write the integral as sum of 3 integrals only. Suppose only 2 singular points inside the region, we write the integral as sum of 2 integrals only. Because of 3 singular points inside the region, we write the sum of the 3 integrals. One integral is for circle C1. Let us suppose the circle C1 contains singular point only 1. So keep that factor in the denominator and take the remaining function as numerator function. 1 by z minus 2 into z minus 3. It is a function. Next, integral over C2. Let us suppose C2 contains singular point only 2 only. So keep that factor in the denominator z minus 2 and take the remaining function as numerator function 1 by z minus 1 into z minus 3. It is a function dz plus integral over C3. Let us suppose this circle C3 contains singular point 3, z minus 3, and take the remaining function as numerator function z minus 1, z minus 1 by z minus 1 into z minus 2 dz on. It is just like this. The closed curve C, inside the closed curve C, the circles C1, C2, C3. Circle C3 on. C1 center is at 1, C2 center is at 2, C3 center is at 3 only. The integral along the given closed curve C is a as integral along C1 plus along C2 plus along C3 only. Okay. But for this method, you need not to draw the diagram also. No need to draw the diagram. Like this, we have written like this only. For each, we can evaluate only. Let us assume that C1 is a circle with center at 1, that's all. C2 is a circle with center 2. C3 is a circle with center 3 only. So from this diagram, 2 and 3 are lying outside only. So this function is analytic inside C1 on C1 only. Then we can evaluate this by using Cauchy's integral formula. This also by using Cauchy's integral. This also by using Cauchy's integral formula. So for each, we are the 2 pi I this is equal to 2 pi I in the numerator function 1 by z minus 2 into z minus 3 at z equal to 1 plus for the second integral 2 pi I 2 pi I in the numerator function 1 by z minus 1 into z minus 3 at z equal to 2 plus 2 pi I 1 by z minus 1 into z minus 2 z equal to 3 on. Now if you substitute the 1, 2, 3 in this, and 2 pi I is common for all terms, minus 1 minus 2, then 1 by 2. Next z equal to 2, 2 minus 1, 1 minus 1, this is minus 1. Next 3 minus 1, 2, 3 minus 2, 1, it is plus 1 by 2 on. Again sum is 0, its value is 0. Now if you apply the partial fractions method, or if you go through this method also, we get the same value only. But better to do the problem in this way only. For this diagram you need not to draw the diagram also. For this problem you need not to draw the diagram also. Diagram is not required. Simply write the integral as sum of the integrals like this, depending on the number of singular points. If you have 2 singular points inside the region, write the sum of the 2 integrals and then evaluate. If you have 3 singular points inside the region like this, we write the sum of the 3 integrals like this only. Or we can use the partial fraction, any one we can use. This is about this problem. So we can do this also in 2 methods, using partial fractions without using partial fractions. But best method is without using partial fractions only. Simply consider like this only. One integral is for circle C1, other integral is for circle C2, other integral is for circle C3, and keep that factor. Let us suppose this point is inside this point is inside this point is inside this, and rest of them are outside the region. So we can evaluate like this. This is about this problem. Next, we go to next problem. This is the problem from complex power series. Here we are asked to write the Taylor series expansion of the function log z. Function log z in the region mod z minus 2 less than 1 only. Now the general form of Taylor series is, f of z equal to summation n equal to 0 to infinity a suffix n into z minus z naught power n, and this an is given by nth derivative of the function at a point z naught by n factorial only. And this is valid in the region mod z minus z naught less than r. This is valid in the region mod z minus z naught less than r, or it is a region of convergence of this series sum, or the values of z in this region, this expansion converges to this function f of z. So it is a ROC of this series sum. Now this is a general formula of Taylor series. Finding the Taylor series expansion of the function at a given point z naught, or in the given region mod z minus z naught less than r, we need to find this quotient. Finding the Taylor series is same as finding the coefficients an. Finding the quotient is same as finding the derivatives only. And this is a simple function, log function. In easy way we can find the higher order derivatives. That is why we use this formula, and then we substitute all this and we simplify, so that we get the one of this option only. The region is mod z minus 2 less than 1. Now let us start the problem. Given f of z equal to log z in mod z minus mod z minus 2 less than 1. From this we can say it is a z naught equal to 2 only. Or since it is in the form of modulus of z minus z naught less than or. That is, indirectly the function is given that at a point z naught equal to 2 only. This function is analytic at a point z equal to 2 only. So we can have the Taylor series expansion only. The Taylor series expansion of f of z about the analytic point z equal to z naught or in the region mod z minus z naught less than or is given by f of z equal to f of z naught plus z minus z naught into f dash of z naught plus z minus z naught power 2 by 2 factorial into f double dash at point z naught plus and so on. Let us suppose this is 1. Substitute f of z naught value in this, substitute f dash of z naught value in this, substitute f double dash of z naught in this and so on. But if in every option only 3 terms are given, that is why we try to find these 3 terms and we simplify only. Let us start with the function f of z. Now f of z equal to log z and its value is f of z naught equal to f of z naught is here 2 equal to log 2 only, which implies f dash of z equal to derivative of log z is 1 by z and its value is f dash of z naught equal to f dash of 2 equal to 1 by 2 only, which implies second derivative f double dash of z equal to minus 1 by z square and its derivative value at a point z naught f double dash at 2 equal to minus 1 by 4 and so on. We substitute all this in this general formula, we substitute all the values and we simplify this. Substituting above all in 1, we get f of z equal to, f of z naught is log 2 plus z minus 2 into f dash of z naught is 1 by 2 plus z minus 2 into z minus 2 power 2 by 2 factorial into minus 1 by 4 plus and so on. Therefore, log z equal to log 2 plus 1 by 2 into z minus 2 plus minus 1 by 8 into z minus 2 power 2 plus and so on. Now this is the expansion of the or Taylor series expansion of the function f of z in the given region. Now this is given in option A only. It is a correct answer. So like this we can add the expansion for a given function. So whenever function is simple function, an easy way to find the higher order derivatives, we use this formula. Otherwise, we go for other method only. The function is algebraic function, we write the binomial factor form, and by using binomial expansion, we can add the expansion. The function is in any standard function. The function is in the form of any one of the standard functions, sine function, cos function, sine hyperbolic, cos hyperbolic, tan function. By using the standard expansion, we can add the expansion of this only. Otherwise, if the function is simple function, an easy way to find the derivatives, we can use this formula only. If it is difficult to find the derivatives, we go for other methods depending on the function. Algebraic function, using binomial, we can add the expansion. The function is transcendental function. By using the transcendental expansions, we can add the expansion. So this is about the expansion of this function in the given region or about an analytic point z equal to 2 only. Now next problem, the Laurent series expansion of e power 1 by z minus 1 about z equal to 1 only. Now for this function, if you want to write the Laurent series expansion, directly we can write the Laurent series expansion because it is a standard function. This is in the form of exponential function. For exponential function, already we know the expansion. Using that expansion, we try to write the expansion of this function about a point z equal to 1 without using the general formula of Laurent series only. The general formula of Laurent series is f of z equal to summation n equal to 0 to infinity a n into z minus z naught power n plus summation n equal to 1 to infinity b n by z minus z naught power minus n. This is contain the positive powers of z minus z naught, negative powers of z minus z naught only. It is a Laurent series only. And here a n is given by 1 by 2 pi I integral over C1 f of z by z minus z naught power n plus 1 dz. And bn is given by 1 by 2 pi I integral over C2 f of z by z minus z naught power minus n plus 1 dz only. It is a general formula of Laurent series only. Depending on the function f of z, evaluation of these two may be difficult. That is why we never use the general formula like in previous problem, Taylor series formula only. Without using this general formula, we try to write the expansion of this function. If it is algebraic function, write the binomial factor and then use the binomial series expansion, we write the expansion only. If it is like this transcendental function, we use the particular transcendental function expansion, we write the expansion. So we try to do this problem by using the standard expansion of e power x only, instead of going for this general formula only. Now let us do this problem. The given function is f of z equal to e power 1 by z minus 1 and the point z naught equal to 1. About that point we need to write the expansion in powers of z minus z naught, that is in powers of z minus 1, z naught is 1 only. Already we know the expansion of e power x. E power x expansion is 1 plus x square by 2 factorial plus x power 3 by 3 factorial plus and so on. So in place of x we write the 1 by z minus 1. So directly we get the series in powers of z minus 1 directly on, which implies f of z equal to 1 plus, in place of x we are writing this only, 1 divided by z minus 1 by 1 factorial plus 1 by z minus 1 power 2 by 2 factorial plus 1 by z minus 1 power 3 by 3 factorial plus and so on. Therefore, f of z equal to 1 plus 1 by 1 factorial into 1 by z minus 1 plus 1 by 2 factorial into 1 by z minus 1 by 2 factorial into 1 by z minus 1 power 2 plus 1 by 3 factorial into 1 by 3 factorial one by z minus 1 power and so on. Now this is the Lorentz series expansion of f of z in powers of z minus 1 or about z equal to 1 only, and this is given in the option 1 plus 1 by z minus 1, 1 by 2 factor z minus 1 power 2. It is given in first option. Therefore, A is correct answer. So with this, all the problems are completed. Now we stop the class here.